Hi children, let's stay positive. Whether it's going to be good or bad, whatever it is, it won't stays for a long time, right? If it is good, yes, obviously we'll be very happy about it. If it is something bad, we'll be feeling bad at the same time. We can have hope, and we have to pray a lot. Our prayers will bring a good result. With that hope, we will be starting our class, darling. And an important note, or I don't want to say this as advice. All of you are having so much of creativity in yourself, as we have seen you in class with so much of uh, other talents, right? So it is the time for you to utilize and make your creativity to come out as an output in your home. So don't stay back at bed for a longer time, and don't waste your golden time. What is the time you have now that you will not be getting back? So that please spend all this time in improvising your creativity as well as enriching your knowledge. Okay, so all of you must be uh, happy, or all of you must be hearing a song, a Kuti story song, right? So we will also start our class with a small story. As you are seeing over here on the Akbar, the king asked a question in his court that left everyone in the court puzzled. As they all tried to figure out the answer, Birbal walked in and asked what the matter was. They repeated the question to him. The question was, how many crows are there in the city? Okay, fine. Have you ever tried to count that, any one of you? We have so much of time now, we can try it out. Okay, so the Birbal immediately smiled and went up to the Akbar, and he announced the answer. He said, there were 21,523 crows in this city. When asked how he knew the answer, Birbal replied, ask your men to count the number of crows. If there are more, then the relatives of the crows must be visiting them from the nearby cities. If there are fewer, then the crows from other city must be visiting the relatives who live outside of the city. Pleased with the answer, Akbar presented Birbal with the ruby and the pearl chain. Okay, so we don't get a chance now to either to visit out of the city or out of the home, or we can't able to call our relatives to our home to stay with us, right? But from this story, what is the moral you have to get? How many of you think about it? Very simple there. Whatever the question you are going to get, you can give any answer to it. That can also be a correct answer, but if you're going to explain it with the proper logic. Okay, so in our class also, if you're going to have any of the questions or answers, all of them are going to be always taken in a correct manner if you have a logic behind it. Think about it, and then we'll get into today's magic with physics. Okay, so the last class we have done how to throw an egg down without breaking it with the help of the science behind it, right? Similar way, we are going to do something with the coin as well as the water over here. So as you're seeing over here, you could able to see a coin when there is a glass which has been kept on it without water. That is, the empty glass has been kept on it. But once the water is going to be poured on it, you couldn't be able to see the coin behind it. Could you able to think of it? Have you ever seen this before? What is the reason behind that? Okay, fine. So I'll try to give you the reason over here. Before that, I can able to make the coin also visible. How could I able to do that? Is nothing but the same coin I've kept over there at the bottom, but now the very few drops of water has been kept on the coin. That is, I made the coin to be dipped in few drops of water, and then I made the glass to be placed on the coin. Now you could able to see the coin over there. What is the reason behind this, which makes this magic as possible? Is very simple. That is, as you learnt in your ray optics, the refractive index of the medium what we are going to have only. So basically we have three cases over here. The first case what you're going to have here is nothing but in the first case we are going to have an empty glass and a coin what you're going to have over there, right? So in the first case, when you're going to look at it, The first case ray will be appearing like this. That is, you're going to have a coin, there you're going to have air, and you're going to have the glass over here, and you're having the air. Then the similar 3 pattern is going to be repeated over here as well. So there won't be much bending of light, as the light is going to travel slightly. You will not be able to see the coin. And you must remember, if the angle at which you are going to look at this coin should be oblique, then you will not be able to see it, right? But when you're going to look at the coin from the other angle, you will be able to view it. And the similar way, when it is going to come for the second case, which is filled with a glass with the dry coin, that is, filled glass is nothing but we are going to have the water. The water is going to be filled inside this the glass, and the light ray is going to travel through it. We all know the refractive index of the glass. The refractive index of the glass is going to be 1.4, and if you're going to look at the refractive index of the water, then that's going to be of 1.33. Nearly both of them are going to have the same refractive index, so that without much bending with the normal, the light is going to move, and you will not be able to see the coin once again over there, right? Yes, when it is going to be away from the oblique angle. But in the third case, filled with the coin, filled as well as the coin is going to be wet. In that case, if you're going to look at it, the medium over here is going to get changed. What is the medium you're going to have over here is going to be getting changed. What is the change we are going to have is nothing but very simple, that here you will be having water now, because the coin got wet now. Water, and you're going to have glass. Both of them are nearly having the same refractive index, not much of the refraction. And when it is going to travel from here, it is going to be water and glass. If you're going to look at it, outside air you're having, which is having the refractive index of 1. So due to this refractive index change, as the air traveling from a denser medium to less denser medium, it will be moving away from the normal, so that you will be able to view the coin easily. So this is what is the magic behind it. Hope so all of you got one more magic to do in your quarantine time, right? So what we are going to do now is nothing but a small recap about what we have done with the last class. That is what we started up with the current electricity. That is what we are going to do. Okay, so what we have started basically is nothing but, what do you mean by the term current? We started with what is current, and the current definition we have done that as rate of change of electric charges, which will be given by Q over T, and the unit of that will be given by ampere. We did, right? And the unit of the charge is going to be coulomb, the unit of the time is going to be seconds. When we are coming for the next term, that is, without these 3 terms we will not be able to understand this chapter, I said. So the second most important term is going to be voltage. The voltage is going to be given by work done by the charge. Hope so all of you remember that pizza example as well as the water example, right? And this will be given by joule over coulomb, that is, amount of work done by 1 coulomb of charge is going to be 1 joule, means that will be giving you what is called as, or what is termed as, 1 volts. Then we came for something called as resistance. Before that, what is the definition for the voltage? How many of you remember? The typical definition according to the book text, what we have is going to be the amount of work done by the charge to move a unit point charge from one point of the circuit A to B. For example, this is going to be a circuit, then from A to B, if you want to move a charge, for that what is the amount of work you have to do? The work done by a unit positive charge to move from one point of the circuit to another point, what is the work? But if I want to tell you that very clearly, in the last class I said, to move from one point to another point, what is the amount of energy lost by the electrons, either in terms of heat or in terms of any other form, that will be termed as the voltage or the potential difference, right? And resistance is nothing but the amount of opposition which is going to be given to the material. Resistance is nothing but the amount of opposition given to the movement of electrons in a circuit. It can be anything, I said. It can be the type of material what you're using, or it can be the nature of the basic nature of the material, or it could be the size of the material, that is the conducting material what you're using, or it could be the surrounding situation as well, that is atmospheric condition as well, either the pressure you're going to have or the temperature you're going to have. So many factors can act as a resistance to a circuit. But out of that we have done, based on the dimension of the conductor, what is the resistance will be having. So what is that we have done is nothing but dimension of the conductor. According to that, what we have done, the resistance will be given by rho L divided by A, where this is being found by the person ohm, and the unit of that will be given as ohm as well, we have done. Yes. And when ohm found about the resistance of the material, he has given us one more relation between this all three, which is called as Ohm's law we have done. Sorry, so that is called as Ohm's law we did, which is nothing but Ohm said that voltage is going to be directly proportional to the current what we are going to have. Whenever, as we know, the proportionality we want to take away, that will be replaced by a constant over there, which is going to be the resistance over here. So V is equal to IR. Vegetarians will always take IERs will always take vegetarians food. I said this can be pronounced as IER, I said, and IER will always take the vegetarian food. So you can remember that in that way, I said. As these two of them are going to be directly proportional to each other, always the curve, there is what is the line we are going to have over there will always be a straight line, I told you, remember. So if you're going to have the voltage and the current graph, that will always be a straight line. So the slope what you're going to find out of that will be giving you the what I told you. So if they're finding the slope of it, you will be having that as I by V. I by V is nothing but 1 by R. 1 by R is nothing but conductivity. All if you remember about it. So all these things we have discussed in the last class. About the current density also we have done. The current density is nothing but J is equal to I by A. I divided by A we have done. Yes. So after that we have done about the mobility as well. So we'll just go for a small recap about the drift velocity and the mobility and the current density, and we will be continuing with the resistance, that is the other factors. One of the other factor which will be deciding the resistance is going to be temperature. So based on the temperature, how it is going to work, and how to find out the amount of resistance associated with a particular color when we are going to use a carbon resistor. That stuff we'll be doing, and with few of the problems. Okay, so when we are going to look into the next slides, what we are having here, as I told you, we are going to do about the relation between current and the drift velocity. How many of you remember the term drift velocity? I'll just go for the next slide. I'll show you what is that, and I'll come back. So when we are going to take a metal, normally if you are going to take a metal, the metal will always be having the free electrons associated with that, that is at room temperature. At room temperature, what is the electron we have inside a conductor will be having a random motion. Random in the sense, in all the directions it will be moving randomly. That means that they don't have velocity. What does that mean? Velocity means a single direction, right? Single direction. Over here, all of them are moving in a random direction. They do not flow in a single direction. That means that drift velocity is 0. Drift is nothing but drifting all the electrons towards a single path, which will be called as current, right? So that drift velocity will be 0 when there is no electric field is being supplied. When we are going to supply an electric field in the sense, we are going to supply a negative kind of electric field to this. If you think, the negative will be repelling the electrons what we are going to have. There is always the electric field what we are supplying will be making the electron to flow in the opposite direction. So if you are going to have apply the electric field towards the right, all these electrons will be drifting towards the left side, as these electrons will start following a single path. So if you are going to supply the electric field, all the electrons will be drifted towards a particular direction. During that time, what is the speed they are going to have? As they are having a particular direction, we will be calling that as the drift velocity. Could you able to understand? This is the same thing we have done in the last class, which is nothing but I told you the force of any of the material will be given by F is equal to ma, and if it is going to be the force about the electric charge, then it will be given by E. QE, you would have been learnt about it in your first chapter, but we are writing that as EE. So if you are going to equate both of them, MA is equal to minus EE, where the E will be, A will be given by minus EE over M. So that's what's the same thing you see over here. Yes, and when you're going to look at it, normally the velocity will be given by, in terms of acceleration, the acceleration will be given by change in velocity over change in time. Then change in velocity will be given by acceleration into change in time. That's the same thing you have here, but instead of the acceleration, this term has been replaced over here. Yeah. Now tau is the average time between the collisions. So if the electrons are going to start moving, there is a possibility for them to get collide with the next electron, right? So what is the minimum time in which the electron travels inside the metal without colliding with the other electron is called as the average collision time. Or between two collisions, what is the time it is going to have? That is called as the average collision time. This time is going to be the same time what we are going to have. Okay, so the delta T is being replaced with the term tau over here, and the delta V is going to be written as drift velocity Vd. So the drift velocity will be given by the formula minus EE divided by M into tau. Yes, did you get this? We have done this in the last class itself. So why I'm saying this to you, you will be understanding that when we are trying to do about the mobility equation in the next slide. So when you're going to look, when you're going to come back over here, we know that very well. What is the relation between the current and the current density, right? What is that relation? J is equal to I by A. Yeah, remember this in your mind, then we'll be utilizing this now. So the number of when we are trying to find out the current will all be given by the formula, what is that? Q over T, right? So we could able to write the current in terms of the other way as well, when we are going to use a conductor which is going to have a cross sectional area and which is going to have the electron which is moving with the drift velocity, and it's going to have a particular thickness associated with that. If you're going to look at it, you could able to see that the Q is equal to N into E into A into D. What is this? A is nothing but area of cross section. As we have done in the resistance, if more area of cross section, the number of electrons will be more, right? So the amount of charge will be more, that is, amount of charge will be directly proportional to the area of cross section. As well as if the thickness is more, then obviously you will be having more number of electrons through a higher thickness. That means that both of them are directly proportional to each other. Then we know that charge of one electron is going to be 1.6 into 10 power minus 19 coulomb. There will be a minus sign, but that represents the negative sign of the electron. Okay, now look at it. How many electrons are there? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, right? Around 16 electrons. I may have counted this wrongly, but the 16 electrons over here. So the total charge, if I'm trying to find, what we'll be writing according to the quantization, how many of you remember in your first chapter? N into E, right? So that's the same thing we are using here, which will be giving you Ne. So the 16 into 1.6 into 10 power minus 19 will be giving you the total charge. That's how we are writing. Q will be given by, for a conductor of length D, and the conductor which is having a cross sectional area A, which is having the charge, that is the charge of electron E, and number of electrons as N, will be having the total charge as NeAD. Did you get this? And as per the regular thing, what is the formula for the velocity? Velocity is nothing but displacement over time, right? Velocity is nothing but displacement over time. So velocity is equal to, I'm writing displacement over time. Now I want to know the time, then how it will become? Which will be given by distance over velocity. So the distance over velocity, that's the same thing you have here, but the velocity of the electron are going to be the drift velocity. Yes, so that's the same thing we have written here. Then we are using the same formula with which we are writing the I here. So I is equal to Q divided by T. The Q value is going to be Ne divided by At, and the T value is going to be T by Vd. When you're going to write it, this 2 will get cancelled, Vd will come up, so that you will be having the equation or the formula for the current as NeABD. Did you get this? So in terms of drift velocity, if you want to find out the current in the problem they have given, the formula what you are going to use is going to be this one only, that is NEA into VD. Did you get that? Okay, so what is next is nothing but why we were doing about it. Now you will be getting the answer for it, right? What is the formula for current? We have done it in the first slide over here, NEAVD. Remember what we are going to do here, the current density we are going to write it in terms of that I only. So what is the one we had now? I is equal to, what is the formula? I is equal to NEAVD, right? But what is the formula for J? I over A. Now substitute the I value for this over here. So what you are going to have? NEAVD divided by A, which will get cancelled, and it will be giving you the equation A is equal to NEVD. So don't get confused that suddenly how we got this one. Okay, this is how we are getting that. And if you're going to look over here, what is the term we are writing? J is equal to NE squared tau divided by M into E. From where it came now? Don't get confused again. Remember about the previous slide. What is the formula for VD? VD is equal to minus EE divided by M into tau. EEM divided by tau. So that's the same thing we are going to utilize over here. EE divided by M into tau. So you're going to have VD is equal to minus EE tau divided by M. You could able to compare it now. So the VD value what you are having, EE tau divided by M, this value we are substituting over here instead of this VD. Could able to see that? So NE is already there, one more E is there, and minus will get plus. So that will be giving you, if you want I'll write it once again over here. So J is equal to minus NE into minus EE tau divided by M. So this minus into minus will become plus, E into E will become E squared, which will be giving you N E squared E tau divided by M. Okay, so that's what's the same thing you're seeing over here, right? Now from this we'll be able to write the conductivity as well. That is, what is the term we are having over here? That is going to be the one which is called as conductivity. Then you must be thinking about it. What do you mean by the term conductivity, right? So how far a material will be allowing the electric charges to flow through it. That nature of the material is called as conductivity. And as we know, conduction and resistance, both of them are opposite to each other. Conduction will allow the number of electrons through that in higher an amount. Resistivity will be resisting the number of electrons flowing through it. As both of them are going to be inversely proportional to each other. Sigma represents conductivity and rho represents the resistivity. Okay, so as both of them are going to be inversely proportional to each other, the resistivity can be written as the inverse of the conductivity, which will be M divided by NE squared tau. Did you get this? Okay, fine. Now we are going to do one more term which is called as mobility. What do you mean by this term? Mobility is nothing but mobility of a mobile carrier, as a mobile charge carrier in a conducting material is defined as the magnitude of the drift velocity per unit electric field. Very simple. Don't get complicated with this definition. Very simple. You are going to supply electric field. As a result of it, the electrons are going to get into motion. So how far they could able to move, how easily they could able to move, that is what is going to be given by the mobility what you are having over here, right? So that mobility will be given by drift velocity over electric field. We know the formula for the drift velocity already. So if you're in terms of the electric field, what is that formula? We know already, which is nothing but VD is equal to, the formula VD will be given by, as per the previous slide, the formula VD is going to be given by what? As I have written over here, EE tau divided by M. So what we are going to have here is nothing but the same formula we are going to have it over here, which is nothing but VD is equal to minus EE tau divided by M, right? So if I'm going to substitute it for this VD, what will be having? Mu is equal to EE tau divided by M divided by E. So what will happen? Will get cancelled. What is the resultant? We'll be having minus E tau divided by m. That's the same thing we have over here, right? Could you able to get that? So what is the term we have over here is trying to tell us is nothing but as the electric field is being supplied, how far these electrons could able to move easily inside the conductor will be telling us what is called as mobility is. Now let's get into the resistor and how the resistance is going to get vary for different materials. Okay, so the Ohm's law is telling us V is equal to IR. We did it already, and according to that, whatever the devices you're going to have, if it is going to have the voltage and the current as directly proportional to each other, all of them will be called as ohmic devices or ohmic conductors. We used to call the conductors which is obeying the Ohm's law as ohmic conductors. Those devices which is not obeying the Ohm's law will be called as non-ohmic conductors. That is, current and voltage graph what you're going to have is going to be inversely proportional. So, sorry, it's not inversely proportional, directly proportional means that is Ohm's law. Suppose if it is not linear, it's not exactly directly proportional to each other. As voltage increases, current will also increase, but the increase or decrease what we are going to have over here will not be linear, means those type of materials will be called as the non-ohmic devices or non-ohmic conductors. Okay, what do you mean by this term? We will be doing few of the examples. As you are seeing over here, what is the limitation of Ohm's law is nothing but you could able to see it does not apply to all non-metallic conductors. What do you mean by this term? Non-metallic conductors is nothing but we know that all the metals are going to be good conductors. As resistance increases, the random movement of electrons will also get increased, that will reduce the current. So the relation between V and I will be always same. Yes, that is the direct proportion what we are going to have. Non-metallic conductors means, for example, we could able to take semiconductors like gallium, silicon. They are non-metals. So when we are going to take such kind of materials, the V and I graph what you're going to have for them, you could able to see that initially as the voltage increases, there is very mild change in the current what we are going to have. As the voltage is going to increase at a particular like a higher amount, suddenly the current start increasing and it gets stable, right? And it is not a linear relation what we are having. Similarly, when you are going to look at the similar thing over here, you could able to see that up to a particular limit, that is in a conductors also, up to a particular limit it is going to be linear. After that it is going to become a non-linear one. That is, as the voltage increases, the amount of electron which is going to move will also be like, whenever the electron moves, it will be liberating the energy in terms of heat energy as well. This heat energy will be increasing the resistance as well. As a result of that, current will be varying, it will not be uniform with the voltage. So that you may have a graph something like this, so that it is not applicable to all of the non-metallic conductors, and it is also not applied to non-linear devices such as Zener diode. What do you mean by this term? Non-linear devices is nothing but those devices in which the input and the output what you're going to have, both of them are not going to be exactly dependent upon each other. So you'll be doing about it better explanatively in the semiconductor devices later. Okay, it is true for metal conductors at constant temperature. Remember, at constant temperature only, but in the circuits there is a possibility for the heat liberation by the working element, so that the temperature may get increased. Because of that, it will not be applicable at those conditions. If the temperature change, then the law is not applicable. So as the temperature changes, it is not going to be applicable. So what are those things only we are going to look at it here. Generally, if you're going to look at it, the resistivity of the different materials will be different. As I told you, resistivity is going to be called as specific resistance as well. Simply, it is going to be the resistance present inside the material when it is going to have 1 meter of length and 1 square meter of area of cross section. Do you remember? So if you're going to look at it, normally the conductors are going to have the resistivity of the order of 10 power minus 6 to 10 power minus 8. When you are going to look at the resistivity of the insulators, they are having the resistivity which is 10 power 18 times greater than the resistivity of the conducting materials. Yes, When we are going to look at the semiconductors are the one which is going to be acting as the insulators at the normal room temperature. When the temperature is increases, or when you are going to have the other factors which is going to get changed, then the electrons in the surface of them, or the electrons associated with the materials, will get into motion based on the different condition. That is why they are having the intermediate value of the resistivity what you are having over here. Okay, so when we are going to look into the resistors normally which has been used, we have two different type of resistors, which is like commercially which has been in use now. So the first one is going to be wire bound resistors. What do you mean by this term? Wire bound resistors is nothing but, you would have been seen this resistors which is used in for example, in this same chapter we'll be doing about few of the circuits. You would have been heard about it, the potentiometer or the Wheatstone bridge, or any kind of bridges, or if you're going to use a resistor in your physics lab, the box type of resistor, except that you'll be having a varying resistor. I'll show that in the next slide. Okay, so the resistors which is going to have a high resistive metal which is been wounded with the wire and which is been coated with the insulating material will be called as normally wire bound resistors, as you're seeing in the first figure over here. Okay, so as you're seeing in the first figure over here, these are called as the wire bound resistors. When you are going to come for the next one, they are going to be the copper resistors. If I want to say that in a very like for your understanding, if I want to say in a laboratory use, or if it is going to be the industrial purpose, we'll be using this wire bound resistors, which is going to be available as a macro level, that is a bigger in size. But this carbon resistors are going to be the small one. All of you most of the time will be busy with your mobile, right? So the motherboard, the computer system, the motherboard on all the circuits, all of them are having the minute circuits associated with them, right? We used to call that minute circuit systems, which will be having the basic of PCB. Okay, so that PCB systems mostly will be having this carbon resistance associated with them. How to find out the color coding of them, what is actually it is made up of, but that steps only we'll be doing now. Okay, so wire bound resistors, if you're going to take that, you could able to see this. I said it's going to have a ceramic, that is I said it's going to have an insulating material which is being wrapped around it. So that insulating material only you're seeing over here, which is a ceramic over here. If you're going to cup open that, and if you're going to look into it, you could able to see that it has been wounded around it with the help of a metal wire, and inside that you are having the high resistive material which has been kept over there. That is why we are calling this as wire bound resistor. In car braking systems also we'll be using ballistic high resistive resistors over there, where we are using the same wire bound resistors only. Okay, in so many industrial purpose also we are using the wire bound resistors only. As you are seeing here, the wire bound resistors is resistor. One best example what we'll be able to see in the laboratory is nothing but the rheostat. As you're seeing here, it will be having the contact pins over here. Through this only we'll be connecting the wires, and as you're seeing over here, there is a metal contact. If you're going to move it, when it is going to be in the starting, it is not going to be in the contact with the metal, so that as we know, the length of the conductor and the resistance will be directly proportional to each other. As the length covers over here is going to increase, the amount of resistance will also get increased. You'll be able to see that when we are going to connect it in a circuit now. So it's just a simple circuit. We have a small LED bulb and we have a key over here which has been connected with the small battery power supplies. All the threes are going to be battery supply, that is power supply. We have three shells which is connected as in the figure. Okay, 1 2 3 cells, and it's a key and it's a bulb. You could able to see initially the length of that is going to be less, so the resistance is less as the bulb was glowing. When it's moving faster, I'm just replaying it again for you. Initially you could able to see that the bulb is glowing here, right? That means that the resistance is less over here. The resistance is less, so it's glowing. When we are moving, length is increasing. As that resistance is increasing, then the current is decreasing and the bulb is going to get off. This is a simple type of wire bounded resistor which we'll be using in the lab. Okay, when we are going to come back to the lab, I'll show you that. And what is the next second type we are going to have is nothing but the carbon resistor I said, and PCB boards I said, right? PC boards. power circuiting boards, we used to call it as. You could able to see these kind of small circuits, and this resistors, you could able to see all this kind of things only we'll be using in all the IC boards and motherboards and all the other type of electronic devices what we are using. This kind of embedding the resistors, this is a capacitor, and all this is what you're seeing is going to be the resistor, and you could able to see few of the chips over here, and we have different type of capacitors also here. So all this combination is called as the IC circuit boards, PCB boards. Okay, so we'll learn about it later on. Now what we are going to do is, this resistors what we have, how much amount of resistance they are going to hold will be decided by the color what they are having on the top of them. That is the carbon resistors resistance magnitude will be decided by the color coding what is on the top of that only. That color coding, with that how to find the resistance, that's what I'm going to teach you in the next slide. So if you're going to look at the color codings will be of different bands. If I want to say that, normally we'll be doing our problems with only 4 bands only, but still we do have 5 band as well as 6 band color coding systems on the resistor. Generally how to find it, I'm just telling you. If you're going to have different colors, what is the first color from the left side you're going to have, that should be taken as the first digit. First digit in the sense, suppose for example the first digit is going to be 1, then it should be written as 1 over here, and the second color will be taken as the band B, which should be taken as the second digits. So suppose if it is the value of the B, black is going to be 0, then it will be 0. And when you're going to take the next one, it's going to be red, right, which will be band, which will be written as a multiplier. Multiplier is nothing but 10 power. So the red is going to have 2, means always whatever the number you are having for the corresponding color should be written on the top of it, 10 power 2. And when you're going to come for it over here, the last one, which will be the tolerance, which should be written in a percentage. Whatever the number associated with that, that should be written in percentage. We'll just look into it bit clearly. You could able to see that black, brown, red. So this is the order in which you have to remember. Black represents 0, brown represents 1, red 2, orange 3, and yellow is 4, green is 5, blue is 6, violet is 7, gray is 8, and white is 9. This is what is the color you have to remember. So the first color represents the figure, that is the 11, 12, 1, 3, like that numbers. The second is going to represent the multiplier, 10 power terms. The fourth one is going to be representing the tolerance level. Now you must be confused how to remember it, right? So if you are going to look at it, you could able to see it over here that, okay, let me take yellow. You could able to see here that black represents 0, black B, B, R, O, Y, G, B, V, G, G, and W. B, B, Roy, BB Roy, Great Britain, Veto, get wet. Veto, get wet. That's what's the sentence you're seeing here. BB Roy of Great Britain, Veto, getting wet. BB Roy of Great Britain. BB, black, brown, red, orange, green, then blue, violet. What is the next one? Green, and we are going to have the white over there. You could able to see that. I didn't say anything wrongly. Yes, correct. You could able to see it here. So you can able to remember the sentence, so that you will be remembering the order of that 0, 1, 2, 3 up to 9 you will be having it. Okay, did you get that? Is that clear? Please try to write it down and then go for it. The same thing, I'm just trying to show it for the 6 band, 4 band as well as the 5 band. Don't worry, you will be asked for only the 4 band max. Okay. So you could able to see brown, which is 1, and red is of what color? 2, so which is 2 we have written, and green is of what number? 5, which will be written as in 10 power I said. And the next one is going to be gold, which is going to be written in terms of tolerance. What is the tolerance of that has been given? 5 percentage. So we are writing the 5 percentage tolerance over here. You could able to understand it, right? And the next one, when what you are going to see over here is nothing but the 5 band what you are having. The 5 band what you are having here is nothing but the black. Before that you must be having a brown, which I missed it over here. So the brown is of 1 and the black and black 0 0 has been written, and for the red it is been written as the 10 power 2 over here. You could able to get that. Similar way the 6 band is also been named over here. Did you get that? If you still having confusion in finding out that, in Google Play Store you will be finding an app for as a resistor color codes. The resistor color code, you can download it in your mobile and you can install it and you can play through it, which means that you will be easily understanding that with 4 band, 5 band and the 6 band. If you wish, you can just try it out. Okay, and what is the next thing we are going to do is temperature difference of the resistivity, temperature dependence of the resistance. Okay, so what it is nothing but I told you that whenever we are going to have the temperature which is going to get increased. Temperature is a kind of external energy what we are going to supply to a metal. For example, if you are going to take suppose the conductor is having a potential which is being supplied to it. As a result of it, it will be having a current associated with that. This current will make the electrons to move in a single direction what you are going to have, right? So the current is going to have the electron which is going to move in a single direction. Suppose if it is receiving the temperature, that is the heat energy which is from the outside direction, and it is going to fall on this conductor, means it will increase the energy of the electron from whichever the part the energy it is receiving, towards that part it will try to move out. For example, you have been seated for the class and you are listening to the video in the mood to understand what is this resistance, temperature, all the stuffs, right? But there is a song, your most favorite song is going to be get played in the TV channel. Suddenly you're hearing that sound. You will be attracted towards that direction. You will try to move towards it, right? So that is the same thing applicable to here. The song what you're having here, there is nothing but the temperature what you have over here. So this temperature will try to drag the electron towards the direction from which it's been supplied. As a result of it, the randomness of the electron will get increased, which will increase the resistance of the material. That is, it won't allow the electron to flow in a single direction, which means that the current is going to get reduced and the resistance is going to get increased. This is what is the temperature dependence of the resistivity or the resistance is. Okay, so how to get the formula, what you have seen in the previous slide, I'm just trying to show it. Let us consider the conductor whose resistances are at 0 degree Celsius and RT at T degree Celsius. What we are going to have, let us consider a conductor whose resistances are at 0 degree Celsius and RT at T degree Celsius, right? If you are going to have RT, how we are getting it? R at T, initially it's going to be R. When it's going to time is increasing, R into T only we'll be writing. Then the increase in resistance, temperature change what you're going to have, resistance change what you're going to have will be given by final resistance minus initial resistance. So change in resistance we have written. Now this change in resistance will be directly proportional to what? What is the initial resistance we had, that one times the time. So that's what we have over here, right? So RT minus R naught is going to be directly proportional to R naught into T. To take off the proportionality, what we'll be writing? There is a constant. That constant is the alpha what you have. Temperature coefficient. This temperature coefficient is nothing but each and every material will be having a capability of allowing the temperature to pass through it. So how far a material could able to observe the temperature or the heat energy will be given by the alpha. This is unique for each and every material, and alpha is constant for each and every material what we are going to have. Did you get this? So when we are going to look at it over here, what we are going to have? So RT minus R naught is equal to alpha RT what you are having here, right? So when we are going to write it as in terms of RT alone, what you will be having? R naught plus R naught alpha T we are going to have. When you are going to take the R naught out of it, you will be having 1 plus alpha T, which will be RT is equal to R naught into 1 plus alpha T, right? So that's what the same equation we have over here. Yes. So the dependence of the resistance based on the temperature. In terms of the graph, when we are trying to do, if you are going to look at the copper, as you are seeing over here, initially it will be showing somewhat a linear character, but when the temperature increases in a higher amount, copper is a very good conductor, but still when the temperature increases, as you are seeing, the resistivity of that will get increased highly. That means that it can't be able to follow a single path, right? And when we are coming for the next one over here, the nichrome is going to be high resistive material. So as the temperature increases, the resistivity of that will also increase highly. And when we are coming for the semiconductors, as I told you, semiconductors are in the need for a energy to make their electrons to get into motion. So as the temperature increases, they will be allowing the electrons to get into motion, which means that they will become conductors from semiconductors. That's why when the temperature increases, the resistivity of the semiconducting material is decreasing in the graph, right? Now we will look into few of the example problems as well as the exercise problems based on this. If you are going to look at it, the electric toaster uses the nichrome for its heating element when a negligibly small current passes through it. Its resistance at room temperature they have given and found to be 75.3. That room temperature, that is initial temperature what we are going to have as per the formula. The T naught what we are going to have is going to be 27, and at that T naught what is the resistance we are going to have is going to be 75.3, right? When the toaster is connected to 230 volt, there is a voltage supply which has been given to it after few seconds to a steady value of current. So we have current and we have the voltage as well, right? What is the steady temperature of the nichrome element? The temperature coefficient, that is alpha value, is being given to us over here. As you're seeing here, this is how a toaster will looks like, right? We have the nichrome wire over here. Initially it's not been connected to the circuit. When it's not been connected to the circuit, at the time what is the resistance you're going to have? That will be called as R naught, which will be 75.3 ohm. And at the time what is the temperature you have? It's going to be the room temperature, which will be T naught, which is 27 degree Celsius, right? Now the toaster has been plugged in. Okay, the toaster has been plugged in, that is we switched it on. When we are going to switch it on, then what is the amount of resistance we are going to, sorry, amount of temperature we are going to have? That's what exactly we need to find, right? The temperature of where it is, what is the steady temperature? That is what's the temperature we need to find. When we are going to come for this, once this is going to get switched on, when the toaster is going to get switched on, it is going to receive a supply of 230 volt, that is voltage is going to be supplied. As a result of it, what will happen? What is the nichrome material we have inside it will receive a high amount of heat energy. As it's a heating material, it will be producing a very high amount of heat. This heat will be increasing what? Resistance. But this amount of voltage, and what is the amount of voltage you are supplying? Initially it will heat up the nichrome in a slighter amount. So initially the temperature will be less, so that the resistance will also be less. But when it is on, after 2 minutes or after few minutes, if you are going to look at it, the temperature will get slowly increase. As a result of it, the temperature will reach a steady state. It will be reaching a steady state temperature. As it's reaching the steady state temperature, the amount of resistance associated with that also should be steady. So that resistance, what it is, that is what we are being we have to find. If you're finding that, then we'll be finding the steady temperature at that point with the help of the formula what we have. So let us write the formula for that first. The formula for that is nothing but what is the formula? We did it in the first one. R will be given by R naught into 1 plus alpha T, or we can write this in a different way as well, which is nothing but, okay, let me write the coefficient over here, because we know that, right? Alpha is equal to, how can we write it? Okay, I'll rewrite this again for you. So what I'm going to do is, just a sec. So I'm going to take R is equal to R naught, I'm taking inside. So what I'll be having, R naught plus R naught alpha T. This T is nothing but difference in temperature. It could be written as T minus the final temperature minus initial temperature, right? So when we are trying to write it like this, then what is the next term we are going to have over here? So R is nothing but this is the temperature at the final temperature what we are resistance at the final temperature what we are going to have. So R you are going to have over here. What is the R value you have over here is going to be RT value you are going to have we are rearranging it I said. So when we are taking this R naught on the other side, R naught is equal to R naught alpha into T minus T naught. So the same equation can be written in a different ways. The same equation can be written in a different modes as well, right? Now when we are going to look at it, what is the value we need to find? This is I'm writing this as T2 and this is T1, as we are having the final steady state temperature T2 and this is going to be T1, and or otherwise you can write this as T2 and TT and T0 as well, as we have taken the R in that way. Okay, so let me write that in the similar way how I have written it for the R. So TT at the final temperature what we are going to have. So what is the thing you are going to have? RT minus R naught divided by R naught into alpha, which will be giving you TT minus T naught. We know this T naught, right? This TT only we need to find. So by taking them we could able to find the value of it. Could able to get this stuff what I'm telling you first, right? So that's what exactly we are going to do. Before that, what is the R naught value we have? That we got it from the previous slide. The R naught value over here is being given as 75.3. What is the R naught value we are having? R naught value is of 75.3 ohm, and T naught value is going to be 27 degrees Celsius. R naught we know it already. What is the value of the alpha has been given for us over here? 1.7 into 10 power minus 4. So alpha in the slide over here is going to be 1.7 into 10 power minus 4, which we don't know RT. For that only we are having the information. The voltage is going to be 230 volt and the current which is going to be over there is going to be of 2.68 ampere. What is the relation between them? V is equal to IR, we know that. So V is equal to IR we will be having, then R will be given by, I'm just writing it over here, then R will be given by R is equal to V over I. So 230 over 2.68 we are going to have, which is going to give us this RT value for us is nothing but 85.8 ohm. I have done it with the calculator, but you should not use a calculator dear. Please go through it and then you will be getting the answer. Please check with yours as well, right? So 85.8 we are getting. If I'm going to substitute all these values, so what is the answer I'm going to get for it is nothing but that is TT minus T naught is going to be giving me the value. What is that? TT is nothing but T naught. What is the value we are going to have? TT minus T naught is going to give me the value 820, right? T naught value 27. When you are going to take it on the other side, if you are going to add it up, the TT value is going to be finally given by 847 degrees Celsius. Please check with that. Okay, and the next example what we have is going to be the resistance of the platinum wire, which is having the resistance thermometer, which is having the ice point as well as the other one is being taken as the cold point. So when the resistor is going to be at the ice point, what is the resistance associated with the ice point is nothing but they have given that as 5 ohm. Okay, and when it is going to come for the hot point over here, at the time the temperature of that is resistance of that is going to be 5.3 ohm, 5.23 ohm. And when it is going to be inserted in both like the bath together, as you're seeing over here, if it is going to be the platinum wire, if it has been dipped inside it at the same time, then what is the resistance of that is going to be 5.795. Calculate the temperature of the bath. We have to find the temperature difference what we are going to have with the bath. That is what we are going to do. So what we are going to do here is nothing but we are going to write the alpha first, because we need to find the temperature only. Let us write the alpha temperature coefficient over here. We are going to write the alpha for it. That is, according to the formula, we will be having that as RT minus R naught divided by R naught into T. But over here, what is the RT we are going to have is nothing but 100. Sorry, and what is the R? This is minus sign actually. And what is the R naught we are going to have is nothing but it is going to be at the cold junction what we are going to have, right? So that can be written as R naught itself divided by what will be having R naught into what is the difference in temperature. Cold bath, that is ice, and the steam they have given. Ice temperature we used to take that as 0 degrees Celsius. Steam temperature we used to take that as 100 degrees Celsius. So when you are going to take the difference, 100 minus 0, which will be giving you 100 only, right? So we have two different kind of equations. This is the general equation for the alpha. This is going to be the equation according to this formula, a problem what we have. If you're going to equate both of them, what you'll be having, RT minus R naught divided by R naught into T is equal to R 100 minus R naught divided by 100 R naught, right? So if I'm going to do this, it will get cancelled. Then what I'll be having over here in terms of T will be given by, the T will go this side and R that will be coming down. So RT minus R naught divided by R 100 minus R naught into 100, right? We know the values over here now. What are the values we have here for the RT? RT is nothing but at the higher temperature, which is going to be 5. RT is nothing but when both of them are going to be dipped inside, which is given by 5.795. This is your RT, this is your R 100, this is your R naught, right? Sorry, this is your R naught. Okay, so RT I have written, R naught is going to be a 5. When we are writing it for the R 100 here, that will be given by 5.23, and R naught is going to be 5 into 100. When we are going to simplify it, what is the answer we are going to have for the T over here? The answer for the T is going to be 3. If you are going to simplify it, 8.65, you can round it off and you can write that as 9 degrees Celsius. Did you get that? Is that is clear? So let's look into the next problems in the next class. Okay, before that, a small recap we have done in today's session about the resistance and the different materials with the different resistivity, and how the temperature is going to affect the resistance of the material. About the mobility we have done. Please go through everything. Our greatest weakness lies in giving up, so don't give up your dream at any cost. To fulfill your dream, you have a very huge amount of time now. Please utilize it and then achieve your dreams. All the best to all of you. Stay safe at home. Okay.